Hello and welcome to lesson 5.1. So in 5.1 we're going to start exploring something called exponential functions, a new type of function for us. So I think a good place to start is, well, what is an exponential function? So it's a function that of course has something to do with exponents if you haven't guessed it, but what it is we'll have some sort of base. This will be some sort of number or constant like 5 or 7 or 1/2 or 8. And the input, the x for this, the variable, will actually be up in the exponent. Now there can be stuff added and subtracted up here and down here and all over the place, but this is kind of the parent function for an exponential function. Okay, so I could have something like 3 to the x, or 5 to the 2x, or things like that. But whenever I have the exponent or the input up in the exponent, the x value, I should say, then we have an exponential function. Now we're going to do a lot with this and kind of shape this whole chapter out of these. We're going to go to another type of function next lesson that kind of pairs with these exponential functions. But the first place we're going to go is very simply to try to graph an exponential function. I'm just going to graph two with you really quickly. You do need to be able to graph these. But I want to show you something with the two that I'm going to graph. Okay? So we'll start with a very simple one, something like 2 to the x. We're not going to ask you to graph too nasty of these. And we're going to graph these pretty much the same way we've graphed everything in this course, at least the first time we graph stuff, is we're going to graph it using an input-output or xy table, a table of values, so that we can have our inputs x and our outputs f of x. Okay, and so I'll go ahead and tell you for these, we kind of want to see how a few different numbers will look. I would like to have like a 0 and a 1 and a 2, but then I also would like some negatives. I'll pick, it doesn't really matter. I'm going to pick some negatives that maybe will have a little more interest to us. That'll be okay. Well, it doesn't really matter. You'll see the shape pretty easily. I'm going to do some of the easy ones. So if I take like a 0 and plug that in, f of 0, whoops, I can't write a 0, is 2 to the 0th power, and anything to the 0th power you should know is 1. So, okay, that's interesting. As long as there's nothing added or subtracted here, then when I have a 0 up here, or anything added up here, if it's a pretty basic exponential function, 0 is going to spit out a 1. Another easy one, let's plug in the 1 here. 2 to the 1, that one's easy. I don't need a calculator, that's just 2. Okay, well this seems pretty easy. Put a 2 in. 2 to the 2, what's that? That's 4. We can probably do these in our head. Ooh, then we get some weird ones. -4, -2. So if I plug in a -2, how is that going to look? Well, this goes back to your exponent rules from your last math course that you took, or maybe one that you took in high school. I can't do a negative exponent. That doesn't have much meaning to me, because an exponent is nothing more than counting how many of something I'm multiplying. So whenever you have a negative exponent, we need to move it from the top to the bottom. Here's what I mean. And so this is like 2 over 1. And so this 2's got to move to the bottom with its exponent, and that changes the exponent from negative to positive. Now I can't leave nothing on top, so I need to put a 1. So this will be 1 over 2 squared, which is 1/4. Okay, that's interesting. And likewise, if I do to the -4th, I'll have 2 to the -4th. I'll have to move that to the bottom to make it a positive exponent. If you don't know that rule, I suggest you'll spend some time back. I think in the very first section is review stuff. I will post old videos from the last math course you should have taken, or the prerequisite for this. For the very first lesson of this entire course, you can go back and watch those, and it has all these exponent rules. And so that'll be 2 to the 4th, which is 16, right? 2 times 2 times 2 times 2. Let's double. 2 times 2 is 4, times 2 is 8, times 2 is 16. Yep. So 1 over 16. Okay, let's try to graph these. Let's go with the easier ones first, like 2, 4. Let's see. So 2, 1, 2, 3, 4. 1, 2. We have 0, 1. We have -2, and it's a 4th, which is just a quarter of the way up. -4, and that is 1/16, so just a smidge above 0. Oh, and we start to see an interesting shape. So these get really, really close to 0, and then kind of explode up and get really steep. Okay, but they never cross 0 here, as long as I don't do something like -5 or something like that, you know. But if I have a very basic exponential function like this, it's never going to cross 0. It has what's called a horizontal asymptote that it cannot cross. Okay, now what's really interesting is this thing starts to curve and shoots up very fast. Maybe you've heard of something called exponential growth. And anytime that we have an exponent with a base that's greater than 1, that's not like a half or a third or fourth or whatever, we get what's called exponential growth. So really quickly, just really fast, just to show you, I'll show you one that's called exponential decay. Graph that and see how that graph looks. And let's just say that my base, instead of being something like 2, is 1/2. And so I'll still do this the same way, have inputs and outputs and make a table. But it'll kind of follow a different pattern. I'll do something really simple. I'll just go -1, -2, 0, 1, 2. Okay, so of course anything to the 0th power is 1, that's easy. To the first power is itself, that's a half. 1/2 squared is 1/4. If I put it to the -1 power, it's going to end up flipping this fraction and it'll just be 2. And if I put it to the -2 power, it'll flip that fraction. Squared will be 4. If you don't believe me, you can put these in a calculator very easily. So I got -2, 1, 2, 3, 4, -1 up to 0, 1, 1/2, 2, 1/4. Oh, it's kind of just, it just flipped it across the y-axis here. It just mirrored it. And so that's exponential decay. So when this base is between 0 and 1, we get exponential decay. Okay, so that's interesting. So exponential growth, exponential decay. When the base is bigger than 1, we get growth. When it's in between 0 and 1, we get decay. It's a very interesting graph. This one also still has this vertical asymptote. It won't go below that. So this end behavior, it just gets closer and closer to 0. That's really neat. Okay, the whole point of this lesson is not to graph these. Yes, I would like you to be able to graph them, but it's really easy. Just make a table and graph them. Now, what I would like to be able to do with this is solve equations. And so we're going to start to introduce some pretty simple stuff, but we kind of need one fact to help us here. So if I have an exponential something like 3 to the x, and that's equal to 3 to the 5, if I have an equation where the bases are equal, then the exponents must be equal. So if I can force things or always have things where these are equal, so 3 and 3 are the same, and if this is equal, that must mean, what does that mean? That means the exponents are equal. X equals 5. So that's not that hard to solve, right? So I could make this a little bit more difficult. I could do something like 7 to the 2x is equal to 7 to the 8. And you're like, okay, well, these two things are equal. Their bases are equal. Therefore, the exponents must be equal. 2x must equal 8. Oh, well, I can solve for x easily. Divide by 2. X is equal to 4. So it's a pretty simple idea. Maybe one more for good measure with the same base, like 5 to the x plus 6 is equal to 5 to the 10th. Oh, it's an ugly 0, 5 to the 10th. Oh, well, if the bases are equal and these two things are equal, that must mean the exponents are equal, and I could easily now subtract 6 from each side to solve for x. X is equal to 4. So these have been pretty easy because the bases have been the same. Now what happens when I don't have the same bases? What happens when I have something like 2 to the x equals 16? Well, what I would like to try to do is I would like to try to get the same base. So I got to do a little bit of thinking and effort here. So 2 to the x is going to be equal to, can I write 16 as 2 to the something? And the answer is yeah, 2 to the 4th is equal to 16. So I can write 16 as 2 to the 4th. Now I've forced it to be the same base. Therefore, that means that the exponents are equal. X equals 4. So you may have to do some careful thinking to be able to figure out how to get things to match up at the same base. I could be even more evil. I could do something like this, like, hey, 25. Okay, let me try writing 25 again. Something like, oops, 25 to the x is equal to 125. And you're like, I don't think I can make this have a base of 25. Can I make them match up somewhere? And this is where it's very useful to know your perfect squares, your perfect cubes, maybe even have some fourths and fifths and sixths and stuff. List out the perfect of those. I wouldn't go very far on these higher ones because it'll get really large. But what I do know is I know that I could write 25 as 5 squared, and then it still has this x up here multiplied. I skipped a step. Maybe I better be more thorough. 25x, I can write that as 25 to the x, and then the 25 I can write as 5 squared. So 5 squared. And when I have an exponent on the inside and outside of, with a single base like this, with the exponent on the inside and outside, they get multiplied, and that'd be 5 to the 2x. So I skipped a lot of steps doing that. I don't mean to. All right, now, can I get this to have a base of 5, maybe? Yeah, that's just 5 to the 3rd power. Okay, so now this is much simple, because 5 to the 2x equals 5 to the 3rd. Their bases are equal, therefore the exponents must be equal. 2 to the x equals 3. And I could easily solve this by dividing 2 on both sides, and x is equal to 3 halves. Okay, all right, maybe one more of these for good measure. And that's really all we want to cover. So something like this: 4. Let's make it more interesting. To the x plus 3 is equal to 8 to the x. So I'll put x's on both sides to make life more interesting. And you're like, I can't make this a base of 8. I can't make this a base of 4. Let's see if we can just break some things down. 4 I know is 2 squared, right? So I'll put it in parentheses so that I know I need to multiply that 2 times this exponent. So can I get 8 to have a base of 2? And this is where it does come in handy to know perfect cube squares and fourths and all that. 8 is 2 to the 3rd power. Okay, so now let's multiply these exponents. So this will be 2 to the 2 times x is 2x, and 2 times this plus 3 is plus 6. And 3 times x is 3x, 2 to the 3x. So now they have the same bases, therefore their exponents are equal. 2x plus 6 has got to be equal to 3x. And I can now just work on solving this. It'd be easier just to subtract 2x from both sides. And 6 will equal 3x minus 2x is 1x, or just x. Okay, so that's not really that challenging, but it takes some practice to get used to this. Trying to force these into the same base, some students find really difficult because they're not really, there's not a systematic way that some people teach this. I'll go ahead and try to tell you the best systematic way I do it. Is I look at the 4 and say, can I make it a base of 8? No. I look at the 8. Can I make it a base of 4? No. Okay, so let's just go to the smaller number. Is this a perfect square, cube, something? You're like, oh, 4. Yeah, that's a perfect square. That's 2 squared. Let's go ahead and just write it as 2 squared. All right, 2. Can I make this a base of 2? And the answer usually is yes, because if it's in this section in this type of problem, we're going to try to make it so that you can solve it. So that's kind of how I think through it. Anyways, that's all I have for you. Try the homework. Email me if you have any questions. Good luck and have fun.